Hi everyone, I just want to make a quick video about the Ajax 2 version 4 board, this one here, and how to get started with putting this inside your Greenpower car. If you want any further information, please navigate to our website, coalescencegp.co.uk, where you can learn more about our team, who we are, our cars, the electronics inside, and some further resources, as well as donation if you feel like we've helped you enough. Under our resources tab, we offer multiple videos about composite processes that Joel specialises in. Also, we have build photos from both our cars, and also all of our electronic resources available for download. So if you want to make one of these, you can, without any charge to me, where you can just download the Gerber files, upload them to JLC PCB, and get all the components from the links on the bill of materials that are included in the hardware zip file. The software will also be regularly updated. However, I must warn you, both the hardware and software, I guarantee you no warranty, and you use it all completely at your own risk. I am not responsible for anything that you do with it. With that being said, I'm going to take you through a general overview, some programming on how to get started, and some tips and tricks, as well as electrical connections to the board. In theory, you should only need 5 electrical connections to get this working. 1, 2, 3, 4, and then your throttle there. So without dragging on for too long, let's get started with the overview. So just a quick overview. Basically, you've got your battery plus, battery minus, motor plus, motor minus. So battery plus, motor minus, battery minus. Then you've got a 24 volt fan pulsed supply here. Your positive terminal is on the left, your negative is on the right. It's also marked just above that block terminal in there. This board uses an ESP32 DevKit C version 4 development board, and you can go buy spares of these, and you can actually remove this by just literally, if you wiggle it out like such. There we go. So that's that there. And when you want to put it back in, please line up the holes, apply equal pressure until it presses fit in. Some connections. You've got your 2 I2C ports here. They are different voltage levels. This one is 3.3 volts, this one is 5 volts. This is the only thing you can connect 5 volt logic level devices to. Please do not connect 5 volts anywhere else on the board. You have a peripheral kind of expansion port. So if you have any extra peripherals you want, you can connect them here. It also has some spare GPIO input-output pins from the ESP that are not used. So you can use these to add a temperature sensor or I don't know, any kind of other sensor. You've got your mode selection pin, your RPM, and your throttle. In theory, all you need to connect other than these 4 connections here is the throttle pin, and then it would in theory work because the motor voltage and battery voltage and current is collected through these 4 pins here. Please do not hold the board by any kind of this heatsink or this capacitor or the SD card module, because they will fatigue and they will break. The SD card module is this here. As you can see, press in, it pops out, press back in, and it stays in. However, you can, with enough force, just take the SD card out. So I recommend, when you're getting ready to race, is putting a small bit of tape, masking tape, duct tape, anything sticky enough on the front here, wrap it all the way over the SD card and back down the other side, just to make sure this can't come out during the race. I believe that is everything, apart from Please do not let this rest on anything metallic. Please make sure your surface that you're working on when you're playing with it is free of any kind of metal shards or metal dust, because as you can see it does sit down and it will bridge the traces. That would be very bad with the magic black smoke, so please don't do that. And now let's get on with programming the ESP. So now we've done an overview of the Ajax board, we now want to upload some code to it. And what we're going to do is open the Arduino IDE version 2. You can download that off the Arduino website, and open the base build.ino. And firstly, if you try and compile the code, it's probably not going to work because you don't have the ESP32 board manager installed. So go to File, Preferences, and you should have this link pasted in here. So if not, please copy the link, which will be in the description. Just literally copy it in text and paste it here as you see. If you have something else here already, press comma and then paste the link in front of that comma. Click OK. And now head to the Board Manager tab, type ESP32, and install the ESP32 by Espressif Systems. Then click on Library Manager and install the Adafruit ADS1115 library, because you probably don't have that one installed either. Where the hell is that? Here, this one here. So if you just copy that up to there, paste it in, and it will come up with Adafruit ADS1X15 by Adafruit. So install that, please. After you've done that, you should be able to verify the code, which is compiling, and it should compile correctly. There we go, done compiling. Before you hit upload, please read all of this information here. This is the warranty exemption and disclaimer. And then also please read all the comments in this section here. It explains what all these different things do. Just to get the board running initially, I will do another code explanation in another video for the whole thing. However, we're just going to speed run the most basic functions of the code. First of all, you've got debug, which you should set to false when you're programming it to the car, or you're going to run it, because you don't need the debug window. But if you're testing the board and just have it on a test rig, then you can set debug to true. This version does not have the debug ramp functions. If your code that you're using has the debug ramp variable, which will be below this part here, just here, please set that to false unless you know what you're doing. Here we've got the safety shutoff, and this is a hard current limit that polls every 100 loops of the code, and if the current reading exceeds this variable here, so 70 amps in this case, for 100 loops of the code, it will shut down the car, because the only case that would happen is if there's some kind of mechanical load on the car that's really using up a lot of current. Then we have the settings, which is where you'll spend most of your time when you're fiddling with this code. As you can see, we've got all the different limiting variables, and we also have the type of control scheme that you want to select. To have voltage limiting, you obviously set voltage limiting equals true. If you want current limiting, you set this variable to false. As you can see, you have the voltage limiting variables here and the current limiting variables here. The resolution of the voltage limiting scheme is a lot smaller. As you can see, it's 0.4 of a volt between all the variables, whereas this is 3 amps of difference. This is the scheme I'd recommend, but this does work, and I will show you later in the data why that is the case. Here we have, these are all current limits, and these are values that override these values here, depending on what state the control theory is in. If we're in the startup, then that means we're in the soft start, and the current limit is 43. If we're cornering, it will select this limit here, which is 38, and if you're in mode 4, which is set by the mode switches, which also select these modes. If you're in mode 4, so this is mode 1, mode 2, mode 3, and then this is mode 4, this is the override limit that overrides everything else here, including the start limit and the pickup limit. It will literally default to that. Don't mess with these, because they are selected by me. They shouldn't really be here, but they should be down in the set of variables, which you cannot change, but I'll leave them here just in case. And then this is the amount of time that you will have to wait on the grid before the soft start is enabled. So you have to turn the car on, wait 6,000 milliseconds, which is around 6 seconds. You can lower this to like 4,000, which will be 4 seconds, but we leave it at 6,000 because if you lower that too much, it won't be able to differentiate between the cornering case and the start limit case. So by having that at 6 seconds, it basically gives the driver 6 seconds to be off the throttle in a corner before coming back on. Otherwise it will default to this, which is not the end of the world, but you can see how that's not ideal. The fan setting, this is inverted, so this is actually about 95%. This would be 0%, and this would be 100%. So we're going to go for 95% fan speed, which is about 50. And all of these are variables you should not be messing with. If you do decide to mess with them, read every single little comment that you get, and also please look at all the other code, because you might be affecting something that you might not be aware of. So other than that, we are now ready to upload the code. So press upload, and it will compile, and then it will tell you how much memory it's used, and it should be around 26% with 6% dynamic memory. That's lovely, and it didn't work because I haven't actually connected it to a board. So when you want to connect it to a board, go to select, type in dev, hit the dev module, and select the COM port that comes up when you plug it in. Hit OK, press upload, and it will upload for you. So I've just, that's what the blue tap was for, so it can sit on the bottom here without moving. This is a little test rig that's made in an old drawer. So you've got the 2 batteries. This looks like they're hooked up in parallel. They're not, it's series. Never hook them up in parallel, big bad idea. And what you're just going to do is you have these are 6 AWG wires, and you've got 2 6 AWG 8mm hole or 6mm hole, can't remember, lugs that go on the end, and you crimp them using a big crimp tool, which I'll put on the screen now, and I'll put a link to the crimp tool in the description. Basically, they go over like that, and you have a choice of M5 nut. Now, these are non-locking nuts, and that's a locking nut, as you can see from the blue insert there. The locking nut is much harder to get on, so you will need a wrench. But the locking nut makes sure that the board will not go through any unscheduled disassembly throughout the race, which has happened before. So you're just going to get a wrench. It's an 8mm wrench. Just torque it on, as so, and you basically want to get it to a point where you start to feel quite a significant amount of resistance, but don't go too much tighter than that. So it shouldn't be able to move if you move it like that, but you don't want any tighter than that because you'll de-thread the shank. So you want to do that for all 4 connections with locking nuts. If you decide not to go with locking nuts, because A, you don't have any, or B, you don't want to torque the living hell out of them, then that's fine. What I'd recommend you do is double up on the nuts that are non-locking. So have 2 per shank, so you have 8 nuts. So as you saw in the software upload part of this video, I'm just going to select the board that's connected now. I'm going to upload the debug program where debug ramp is set to true, which basically means that when the isolator switch is turned on, the motor will start spinning. So I'm going to press upload now. This is an acceptable micro USB type B cable. It's a Logitech one from something else that I bought. So it's now uploading. It's going to flash. It's done. Cool. So I can unplug that now. And even though we don't have any of the throttle connections, mode connections, RPM, any of the kind of peripheral sensors connected, this program is still going to run the motor just to check that the board works. So just give it a second. So it's just ramping slowly up. So you can imagine if your car was on the ground, this would be very bad. So please don't use this program if it is. And once it's at 700, it will hold. But even if now I go to plug it back in as it's running, so my computer is now connected. You'll see if I open the serial port that I'm still getting debug data. And you'll see the battery voltage is currently 25.5 volts. And it's currently running motor voltage at 17 volts, which is about 700 PWM if you scale it to 1023. It's drawing about 1.5 amps. None of the inputs I've changed, but there you go, PWM 700, and that's the motor working. So just to quickly go back over the throttle connection, which is this JST here. I just want to make people aware of the difference in setup you need on the board to make analog throttle input, i.e. a twist grip throttle or a potentiometer or a Magura throttle, work with this board. By default, if I'm making this board for you, I will solder these 2 resistors in. These are the only 2 resistors where it's either you have them in or you have them out. When you have them in, that's for a push-to-make button, digital off-on kind of button throttle setup, where you literally just, the driver only has to press one button and the car does all the thinking for you. If you want to have an analog setup where the driver can use a twist grip throttle, you need to remove these 2 resistors so that they aren't pulled up to 3.3 volts. When you're operating this in digital mode, so when these 2 resistors are in the board, you actually don't need this pin here because the pull-up is done for you on the board already. So actually, although this is being wired, we don't necessarily need this wire, but we need 3.3 volts if we're wiring it to a potentiometer / twist grip throttle, hence it is included in this connector. So now I'm going to show you the telemetry. As you can see, I've got 2 Arduino programs open here in split screen mode. I've got the transmitter and I've got the receiver. The transmitter code is slightly more complicated because we have to offload the data from the motor controller and then packet it up and then send it to the right address. Whereas with the receiver, we literally just grab the data and then print it to the serial. So firstly, in the transmitter, all of these libraries should be included with your version of the Arduino IDE. You shouldn't have to do any library management. The same board management applies because we are using an ESP32. So if that file preferences, this thing here still needs to be there. That all still applies. The pins, please not change these because they are hard set on the PCB. If you're designing your own PCB, then you might want to use different connections. I don't know. And this is a 433 megahertz version of the telemetry. You can buy the RA-02 AI Thinker LoRa transceiver, and you can buy that in like 896 megahertz and 915 megahertz models. And if you do buy those modules, then you will need to change this value to correspond. You can change this code so that you can get more data to come through the I2C port, but that means you'll have to change all 3 versions of the code. And what I've got in this setup is literally all the main code build on the motor controller is doing is printing out the amp hour reading that it is getting, because that is a direct measure of our battery capacity usage. And what happens is it gets sent to this transmitter module via I2C. So this is waiting to hear for an I2C event. And when it hears an I2C event, it will then send the value via LoRa, via the LoRa dot packet, begin packet stuff, which is using the LoRa dot H library. It also sends the length of the message, and it sends the address at which it came from. And the addresses are currently set to 0xAA, and the destination is this code here. So you can see here it's 0xBB is the local address here, and the local address here is 0xAA, and it's inverted for the corresponding codes. You don't need to include y.h on this code because we're not doing anything over I2C. And literally what's happening here is when it receives a LoRa message, it reads out the length, address, and the random bit that gets sent as well. I don't really know what it's for. It's just an extra little quirk of the LoRa.h library or whatever. So we get rid of those bits of data because we really don't need them. And then we print out the rest of the actual information that we need, append it to a string, and then we will print it on the serial port. And we will keep printing it until we receive a different instruction. So it's just literally going to keep sending on the serial the most recent value that it's got, because it's going to drop out of range. So you're just going to keep getting the same value, the same value, the same value, and when the car comes past on the pit wall, it will receive a new value and it will update onto the serial port. So that's how you know you're getting the most recent value. With this one, you literally just upload it, plug it in, then leave it. Don't do anything with it. You're not reading the serial port or anything on this one. The serial.print messages are purely for debug and just to make sure that it's working when you're testing things out. The receiver, however, you are going to open the serial port using this button up here, and you need to set the baud rate to the same as what has been set here. So serial.begin 115.200.00, and that's what you need to set the serial monitor rate at. If you don't want to open, if you have a laptop that's not the one that you're using to program them, and you want to, on a race day or something, you've got your own laptop, or your friend's got a different laptop that doesn't have the Arduino IDE, what you can do is download Putty off the internet, which is a very old piece of software, but it's great. And all you have to do is click serial, select the COM port, which will show up in your device manager. So here we go. It will literally, when you plug it in, it will come up as ports in LPT, and it will tell you what COM port is being used. For example, 3. It would also show you up here, but that's not the point. And then you also need to set this to 115.200, and open the port, but it's not going to work here because I don't have it attached. That is literally all you need to do. So upload this code to one board, upload this code to another board, and just make sure you have the right corresponding addresses. You can change these. If someone else is using the same addresses on the day, that would be very unlucky, but I'd recommend changing these. And then just open a PuTTY window or the serial monitor here, and it will show you the data from the receiver. So you've now got your data off your Ajax 2 board. It's on an SD card, and you want to read it and actually read the data effectively to decide what you need to do with your car. So there are two ways of doing this. One is using Excel, and one is using a program that we have internally developed, definitely not using ChatGPT, such that it will do all the graphing for you, and you will see why it's a lot better. But we'll do Excel first, just because it's the first principle, I guess. So you should have a text document that comes out, and it should look something similar to this. Now what we're going to do is we're going to go into Excel, we're going to go to Data, from text/CSV, and we're going to select that from the desktop. A really important step here is to not select based on the first 200 rows. We do not detect data types, because otherwise we'd get a lot of integer values based on all the zeros when the board is first switched on. So load that data, and that might take a little bit longer on your computer. And what you're going to do is, we don't want these column headers because we already got column headers we want, but Excel doesn't know what any of this data is, what type of data it is. So we're going to go across, drag across, Control Shift down, Control C to copy, move to another sheet that will already be made, Control V, and then do exactly the same thing where you drag across, Control Shift down, but only on the actual numbers, and press Convert to Number. And this tells Excel that all of these things are actual numbers and not currency or any of the other types of data that you can get from here. So what we can now do is actually just go ahead and plot the data. Now this is a practice session from Castle Combe 2023. So this is real data from a car. As you can see, it's pretty unreadable, should we say. You can tell that, we're using a little bit more than 30 amps on some of the peaks. But you can go to chart, change chart type, combo, and then it should automatically do that. You can change what axis some things are on, so you can move the current to another axis. But for this, we'll leave them on the same axis. Now you'll notice that didn't take too long. However, this is not a very big data set. I mean, it might look like it is, but really this is not that ginormous. So a megabyte of data is a big Excel sheet. Sometimes that last step where I went to change chart type, combo, and then change the layout of the graph, that is a particularly involved and intensive process for Excel. And depending on what computer you have, that might really not work. And sometimes on this computer, it does not work either. So what you'll need to do is, I'll just delete that. If it's not working, you need to select data that you want before and just drag down a few values, like literally 10, 20 values. Go to do the same thing where you go to scatter. Now it's going to look really weird. And what you can now do is change chart type, combo, and that still looks really weird. But now it's already converted to a combination graph. You can scroll this all the way down to the bottom. Right, we'll just do it to there. There we go. Brilliant. Scroll all the way back to the top, and there we go. The graph has been generated. So by selecting a small amount of data, changing it to a combination graph, and then dragging down, it will kind of bypass this weird glitch that Excel has. That's just a really important detail. Now, as you can see, this isn't, it is good. You can see what the car's doing. You can see the motor voltage limiting is happening here, but you can't really like zoom in. You have to zoom out on XL and do that, and that makes your computer lag, and it's just not a very good interface. So what we've done is we've used MATLAB to create an exe file which you can install. This will be available on our website, and all you have to do is double click enigma_v1_installer.exe. Double click that, say yes. Say yes to any administrator privileges thing. Don't worry, we're not hacking your computer. You can set your own location if you want, but we're just going to say yes. And we can add a desktop shortcut. And it will ask you to install the runtime. And this is really important. So if you don't have MATLAB already installed on your computer, you will need this runtime. If you have it installed on your computer, you will still need this runtime because it allows the application to run without MATLAB open. Which is really important because if you don't have a MATLAB license, how would you run a MATLAB app without the runtime? So this is a free runtime that allows anyone, regardless of whether they have a MATLAB account or not, they can run the app, and MATLAB runs all the back-end stuff. So we're just going to wait for it to install. You clicked yes, next, begin install, and this process will take a while because you're not actually limited by your internet speed. You're limited by MATLAB's ability to consume the information. So yeah, I'll be back when this is done. So we've come to the end of the installation process. You can hit close. So now we've got the app installed. I closed the installer once it had finished. And you'll have an app here with the name Enigma, hopefully. Or you can go into search if you haven't selected the desktop icon, and you can just get it from here. So double click. There you go. It will load our logo, and then it will prompt you to select a data file or text file. And then it might take around 30 seconds on the first time that you try this, but that's a lot faster than the entire process we went through to get this graph. So ignore the RPM because we didn't have the RPM sensor working. It was glitching out. But as you can see, we've got a new text file that's been interpreted into a graph. And there's lots of different things you can see here. You can select data that you want to see, and it will automatically scale to that data. So, for example, we want to see the relationship between the battery voltage and the motor voltage. In this case, you can see we had motor voltage limiting, not in its final form, so there was a little bit of tuning that was done after this race to get it absolutely bang on, but this is just an example data sheet. As you can see, we're limiting the voltage here for a constant speed, and you can see it goes up. We're on a different voltage limit here, and it goes up again, we're on a different voltage limit here. If you select mode, you can see that we're in mode 10, and then the mode 20, and then mode 30. Now, in reality, we were actually in mode 1, mode 2, and mode 3. I've just multiplied the value for the mode by 10, so that is visible on this axis here, because otherwise it would be down here like mode 1, mode 2, mode 3. So it's just multiplied by 10 so you can actually see what mode you're in. As you can see at the start here, mode 0, this is when the car is stationary. And in this section here, you can see the acceleration happening, the soft start. You can see the motor voltages slowly climbing to a crescendo there. If we want to see that in more detail and how that control theory was enacted, we can literally just select the zoom tool, select that frame, and then we can actually see in more detail how the motor voltage was ramped. Now, you might be curious, oh, how much power did we draw? Well, turn on the current, and you can see the sawtooth of the current limiting scheme, which is not as accurate as a motor voltage limiting scheme, but you can see how it is allowing the car to stay at a relatively constant current draw of 45 amps on this average plane here. If we select Show Averages, what you can see here is the average data for each variable that's listed here within this window. So if I was to press OK and press Home, and I press it again, this is now how many watt hours did we draw during the entirety of that practice session, how many amp hours did we draw during the entirety of that practice session, etc., etc. You get the message. If you want to see, what's quite useful actually is seeing the average current draw for a lap. So if we select, we go from say this low peak here to this low peak here, and we literally just go drag from there to there and press Show Averages, it will now show you that you used an average of 24.45 amps. So there you go. This is in F24 Plus as well, so we do have a little bit of a higher current draw than F24. So that's pretty much it for the software. It's incredibly useful. It's a massive upgrade over Excel. You can use other tools like VBox, which I know some teams use, but you do have to pay for VBox unless you get a totally legitimate key for it. So we decided to develop our own software that kind of does exactly what we need it to, with the showing averages and the current draw and the capacity. Because if you press Show Averages, your amp hours or your watt hours, you know exactly how much power you drew from the batteries in that session, just by clicking Show Averages right there and then. And that did not take any time at all. So there you go. Just one more thing worth mentioning. If you want to change what data you're recording, then you're not going to be able to use the app, because the app is set up to accept the data that is currently programmed in the online available code. However, it would not be too, I can supply the source script. If you have MATLAB, you can edit it, and it is not too hard to understand. It just requires a few arrays to be edited. But in terms of editing the raw text data and getting more data onto that data file, regardless of what the app is going to do, all you need to do is where it says append title, so you can do a Control F search for append title, and it should bring you to the initialization and then the actual calling. You got time, battery voltage, motor voltage, current, RPM, PWM, amp hours, mode, TPOS. If you want to add something, you can just go, I don't know, watt hours. I don't know why you would, because this is calculated for you in the data analysis software. But you can do, for example, watt hours there. And then you need to go to the append data function, which is found down here in the save data function. And you can see what there is a new line, and then string data, a comma, string data, comma, etc., etc. Go to the end of that, insert a comma by doing so, another plus, and then type in the string identifier plus the new variable that you've just created. Obviously, you will have to now calculate the actual watt hours somewhere else in the code, creating a new function or something. And in doing that, you will now save watt hours to the text file, so it will generate a new header here plus an extra bit of data there. It's important that you have the same number of headers as you do individual bits of separated data. Anyway, that's just a quick public service announcement.